EMS. So you have 25 minutes for your presentation. Please share your screen. Yes, we can see your slides. We can hear you. So please go on.
Okay, great. So I guess you also can see the slides in full screen. And yeah, then thank you very much for giving me the opportunity to present today the Higgs studies at both ATLAS and CMS. And so as a pre-remark, let's briefly talk about the standard model Higgs boson and how it was discovered. So, I mean, you are most likely aware that the standard model of particle physics is remarkably successful in both describing and predicting experimental results. And it was completed by the discovery of the Higgs boson in 2012. On the right-hand side, you see one of the two discovery channels, the diphoton channel, with the full run-2 ATLAS dataset. And you see why this channel is so liked, because you have a rather small background and this nice and clear Higgs peak above that. So far, the main production and decay modes of the Higgs boson have been observed, and we have, since the discovery, entered the era of precision measurements, for example, for the Higgs potential and targeting rare decays. Despite the strong success of the standard model, there is evidence that there must be physics beyond the standard model, Bsm physics. For example, in the standard model, we don't have an explanation for neutrino masses, and there is no candidate particle for dark matter. So today I'm going to give an overview on recently published ATLAS and CMS results, targeting standard model and Bsm physics alike, and all of these analyses are based on the full LHC run-2 dataset. So as I mentioned, I will also cover Bsm physics, and for many Bsm processes, the Higgs boson or Higgs bosons play a crucial role. For example, there can be additional Higgs bosons in enlarged Higgs sectors. There can be invisible decays of the Higgs boson, for example, to dark matter candidates, and there can be contradicting properties of the 125 GeV boson, contradicting the standard model predictions, for example, CP violation or changed cross sections and branching fractions. But before talking about Bsm physics, the first analysis I'm going to present today is an ATLAS analysis referenced here on the top right, targeting the Higgs boson production cross-section in the Higgs to tau-tau decay, which has the largest leptonic branching fraction with about 6%, and is therefore a unique way to study the Yukawa mechanism. The measurement is, however, complicated by the presence of neutrinos in the tau lepton decay, and the main background in this search is from the Z to tau-tau decays as well as TT bar. This analysis uses the simplified template cross-section framework, STXS, in the stage 1.2 with a reduced set of bins. And the target of this framework is to maximize sensitivity by minimizing the theory dependence. And the bins in this framework are defined to enrich events of a certain production mode. And this you can see here on the right in the schematic, where you have the production modes on the left, the STXS bins in the center, and the analysis categories on the right. And these analysis categories are defined based on the STXS bins targeting the individual production mechanisms. Recently added are the TTH and VH categories, and the events of a certain production modes in this category are enhanced using multivariate techniques. The Z to tau-tau background is constrained by both simulations and data in control regions, where the control regions are defined orthogonal to the signal region, selecting Z2 lepton plus additional jet events with a dilepton mass above 80 GeV, leading to over 99% purity. And this is used to emulate the Z2 tau-tau by using the embedding technique. And additional weights from simulation are used to account for kinematic bias, normalization effects, lepton triggers, identification and reconstruction efficiency. And all of this considers also the lepton isolation. And here on the right-hand side, you see the effect of this embedding technique, where on the left, you have the Z2 lepton, and in green, you see the result for the Z2 tau-tau using the technique where one of the leptons in the Z decay is replaced by a simulated tau. And you see that it agrees well with direct Z2 tau-tau simulation. This technique is validated also using simulated samples for all background processes, while the top right plot is a combination of several selection categories. On the bottom left, you see one of this distribution for the vector boson fusion production in the tau leptonic, tau hadronic final state. and the observed discrepancies agree well with reported Z plus jet measurements. With this analysis, the total proton to Higgs to tau-tau cross-section can be measured, and the result is consistent with the standard model prediction within uncertainties. And it is also measured per production mode, which you see here on the top left, as well as the combination on the bottom with respect to the standard model prediction. And the overall compatibility with the standard model is 88%. With this result, also the observation of the vector boson fusion production mode with a significance of 5.3 sigma can be constituted, as well as evidence for the gluon-gluon fusion with about 4 sigma. The cross-sections are also measured in terms of the reduced set of bins of the stage 1.2 of the STXS, showing good precision up to 24% in this bin here in the VH and VBF production mode with a large digit mass. And this is as well in agreement with the standard model predictions. The second analysis I'm going to show to you today is also targeting the Higgs to tau-tau decay, but mainly analyzing the CP structure of the Yukawa coupling. As in the standard model, the Higgs boson is predicted to be CP even, so a scalar, and any kind of deviation from this would immediately indicate new physics. A fully CP odd, so pseudoscalar, is already excluded, as well as CP violation in a coupling to the vector bosons. For this analysis, the H-tau-tau couplings are decomposed into CP even and odd parts indicated by these kappa parameters. And then the effective mixing angle phi tau-tau is defined through its tangent as the ratio of these parameters. And you see its effect in the top right plot by a shift in the phi CP distribution, which is the angle between the tau decay planes. This phi tau-tau angle is quite important, as a value of 0 would correspond to a pure scalar coupling. And for example, the next to minimal supersymmetric standard model allows a value up to 27 degrees. Also, other BSM models predict non-zero values. The analysis here includes fully hadronic final states from the tau decay, as well as tau H, tau mu final states. As in the previously shown analysis, the Z2 tau-tau contribution is estimated using an embedding method based on Z2 mu decays, and the backgrounds with jets misidentified as tau leptons is determined from data by selecting tau hadronic candidates in regions where there shouldn't be any tau leptons. And 2 MVA discriminants are used to separate signal from major backgrounds in the tau H and tau H tau mu final states. And these have 3 classes each: the signal category, the Higgs category, and 2 background categories targeting genuine taus and jet fakes. On the bottom left, you see the genuine tau category, the background category in the tau mu tau H final state after the MVA-based selection. And on the right-hand side, you see the signal category in the same final state, where in each of these windows of increasing BDT score, you see the phi CP distribution, and you see that the MVA technique is really quite powerful in both discriminating CP even and odd contributions, as well as, as you see on the bottom, increasing the signal contributions. The final result of this allows to distinguish CP even and odd couplings with a significance above 3 sigma. And the result observed is, as you see here on the top, compatible with the standard model prediction within the uncertainties. And as a cross-check, also the Higgs production signal strength modifier mu tau tau, as you see on the top right here, has been calculated, and the observed value of 0.8 is also consistent with the standard model within uncertainties, where the red star here indicates the standard model prediction. So from the standard model going to rare decays of the Higgs boson, this search here targets invisible decays of the Higgs boson, where the invisible decay products could also target a dark matter candidate being the mediator. And the search for weakly interacting massive particles, WIMPs, indicated as chi in these Feynman diagrams here, relies on the associated production with Z boson to search for missing transverse energy. Furthermore, the Z boson is required to decay leptonically for a clean signature. Since dark matter must be massive, there's a strong argument to be made to look for it in interactions with the Higgs sector. And in this analysis, there are several benchmark models targeted. First, the decay of the standard model like Higgs boson. Second, a simplified S-channel dark matter production, for example, here. And third, 2x doublet model with additional pseudoscalar models. So here and here on the right. The interpretation of the limits from the first two of these are then compared with direct dark matter detection experiments. So dominant background contributions for this search originate from vector boson production, as well as some non-resonant WW or TT bar contributions. And then there are smaller contributions that are labeled other. In the plot here on the right-hand side, this other is not listed because it's negligible in the signal region. So the background prediction is compared to, the data is compared to the background prediction and the signal hypothesis in a simultaneous fit of the signal region, as you see here, which you see here on the right, and control regions. And the Higgs to invisible sensitivity is increased by using a BDT, a boosted decision tree, providing one single output variable. And this is used in the EMU control region, as well as the signal region, which is shown in the plot for the final likelihood. And you see that the signal hypothesis the contribution is indeed increased with increasing BDT score. So far, the data is in good agreement with the expectation, and the best fit constrains the branching fraction of the Higgs to invisible to be below 18%, which is also the expectation. And the improvements made in this new analysis lead to expected limits, so sensitivities, 45% better than the projection of previous techniques scaled to the full run-2 luminosity. So this is quite the huge achievement. And these results can also be transferred using the Higgs portal model to compare with direct dark matter detection experiments, which you see in red and blue here in the plot on the bottom right. And you see that it's quite compatible with direct searches. The interpretation of results is also done in terms of the 2x doublet model plus additional pseudoscalar, as you see in the top right plot, in terms of the value of tangent beta, which is the ratio of the vacuum expectation value of the two Higgs doublets, as well as the pseudoscalar mass MA. And you see the significant improvement with respect to the yellow 2016 result, also helped by the inclusion of the BB-initiated production. The dark matter results are compared to direct searches, as you saw on the previous slide, using, for consistency reasons, the 90% confidence level. But keep in mind that the translation is always a result of some models, so making assumptions, in this case that the decay is kinematically allowed and that the WIMP is a scalar or Majorana fermion. So these results are model dependent. You can also assume simpler, more basic models, and the respective limits are shown here on the top right. And again, you see the significant improvement with respect to 2016 results in yellow. Overall, as just mentioned, there are significant improvements based on the new analysis techniques compared to the previous results, and the dark matter results are competitive with direct searches. The next big block I'm going to talk about is the search for di-Higgs production. Today, I'm going to focus on recent results of the searches in the 4B and BB tau tau final states, referenced here again on the top right. There are, however, lots of additional analyses that I cannot discuss today, and they are referenced here in the orange box. So the 4B final state has the advantage of featuring the largest branching fraction with about 34%, and the search is conducted in for the non-resonant production in the resolved and boosted channels, targeting different production modes. And the boosted analysis is the first one to use the particle net algorithm to identify the BB bar merge jets versus standard model background, for example, TT bar. And the BB tau tau analysis is done in the resonant for the non-resonant and non-resonant production, targeting both of the gluon-gluon fusion and vector boson fusion production modes. And it features the best expected limit to date, profiting from a reasonable branching fraction and a rather low background. The vector boson fusion is quite important as it allows to assess the VVHH coupling here on the bottom right, as well as the VVH, in addition to the tri-Higgs coupling. And in the standard model, there are large cancellations between the tri-Higgs coupling and the box diagram, the two left diagrams, as well as the VVH and the VVH here, second from right, and VVHH diagrams. These cancellations are not present in some Bsm theories, so there's quite a discriminating power. And also the tri-Higgs coupling is a critical input to the standard model as it tests the Higgs potential, and this has implications on the vacuum stability. First, discussing the 4B analysis. In the resolved channel, there's a large multi-jet background from QCD and TT bar, and this is estimated from a control region. And both the control and signal region are split into 3 and 4B categories based on the deep jet algorithm. And the background in the 4B signal region, which you see here in the plot, is modeled from the 3B signal region with a transfer factor, which is determined from the respective control regions. The differences in observables are then modeled based on a boosted decision tree, which is trained in the control region separately for both different production modes. As you see, so far for the vector boson fusion selection, the background describes the data quite well, and you see the signal hypotheses here on the bottom, enlarged by significant factors to make them visible. And on the bottom, you see the boosted analysis where the particle net, a jet substructure algorithm based on a graph neural network, is used. And it's also used for the jet mass regression. The background in the signal region is estimated from a simultaneous fit with control regions, where the transfer factor is calculated in sidebands of the subleading jet above or below the Higgs boson mass, and validated in sidebands of the leading jet with the signal region masked. In the plot on the left, you see the medium purity signal region, which means that both leading jets must pass the medium working point of the particle net algorithm with these selection efficiencies. And again, you can see that the background hypothesis describes the data rather well. On this slide, you see the results for the 4B analyses. So far, no evidence for signal is observed, and the searches are mostly limited by statistics. For the resolved analysis, you see the result here, where the limits above the pink theoretical prediction are still allowed. And this leads to the ranges of the kappa parameters you see here. And in terms of the standard model, assuming that this is what we are looking for, the gluon-gluon fusion production cross-section is constrained to be below 3.6 times the standard model prediction, which is a very, very low value already. For the vector boson fusion, this value is about 226 times the standard model prediction. In the boosted analysis, similar limits can be calculated. Again, the part above the red line is still allowed. And the observation here excludes a value of kappa 2v equaling 0 at 95% for all remaining allowed values of kappa v. And you can see limits in terms of both of these parameters here on the right-hand side, where the part between the bands is still allowed, and the red diamond is the standard model prediction. And the small dotted lines are respective vector boson fusion production cross-sections. In the BB tau tau final state, there are final states allowed that include at least one hadronically decaying tau, and there are 3 signal regions based on different triggers. MVA discriminants are used to distinguish signal and background, and the same inputs are used for the resonant and non-resonant production, where backgrounds with true taus are simulated, and from fake taus, there are data-driven methods, and a dedicated control region is used for the normalization of the Z plus heavy flavor jet background. And in the non-resonant analysis, standard model kinematics are assumed, while the resonant analysis targets a narrow width scalar with a mass of 251 to 1600 GeV. On the right-hand plot, you see the signal region in the tau H final state, assuming a 500 GeV new particle. And you see on the x-axis the parameterized neural network score, and again, it increases the signal content for larger masses, larger scores, sorry. And the largest excess is seen about at 1 TeV with 3 and 2 sigma local and global excess respectively. And the non-resonant di-Higgs production limits the cross-section to below 4.7 times the standard model prediction, which you see here, and other analyses are referenced here also in the summary plot. This is the best expected limit, so the highest sensitivity to date. Coming to a diphoton search, so looking for new diphoton resonances is making use of the clean signature in that channel. Remember, it was one of the Higgs boson discovery channels. So it allows for precise reconstruction to separate standard model background from a potential signal. The interpretation is then done in two different models based on a common event selection. So it's searching in this diphoton channel for a new spin zero state X, which is predicted by many models with an extended Higgs sector, or a spin 2 graviton, in this case, the RS1 model. The largest background for this search is non-resonant diphoton production with smaller contributions, including jets. And the relative contributions are estimated at two-dimensional sideband method based on passing or failing of the photons of the tight photon identification and some isolation criteria. And you see this here in the right-hand plot, where you see the individual contributions, and in black you have the data. The analytic form of the background is fitted in diphoton simulation and photon jet events from a control region, performing the fit above 150 GeV to allow for enough events in the sideband. And the upper edge of the fit here is determined by having enough events for a stable fit. And you see that this leads to a quite spiky background, let's say. And this is smoothened to mitigate the impact of statistical fluctuations due to limited number of generated Monte Carlo events. And the smoothing is based on the functional form determined in simulation and the spurious signal, which is the signal yield fitted in pseudo experiments. And the smoothing techniques leads, as you see here, to smaller and fewer fluctuation, yielding an improved, up to 28% improved actually, limit on the cross-section times branching fraction. The data overall is well described by the background only fit, which you see on the bottom left plot. And the excess with the largest local significance is at 684 GeV with about 3.3 sigma. And global significance, depending on the model, is about 1.3 or 3.6 sigma. So the observed limits, which you see in the right-hand plot, agree well with the expectation. And in the RS1 model, the graviton mass can be excluded below 2.2 TeV, larger, however, for different choices of the coupling strength. And in all cases, a narrow width approximation is used. And a fiducial cross-section is also used, which is the overall cross-section times the acceptance, where the acceptance closely follows the selection criteria. So the last analysis I'm going to present today is a search for additional neutral Higgs bosons. In this case, a heavy neutral Higgs boson capital H here in the center, decaying into the 125 GeV boson small h, and an additional state HS, assuming that this decay is kinematically allowed, and that the subsequent decays are into a pair of tau leptons and B quarks. Such a Higgs sector is, for example, predicted in the NMSSM, where we have an additional Higgs doublet plus an additional singlet, leading to 7 physical Higgs bosons, which you see here on the right-hand side, where these 3 neutral CP even states are targeted in this analysis. And the HS state is assumed to have significant mixtures from the singlet, and therefore suppressed couplings to standard model particles, and therefore the preferred production is in the decay of the capital H. This is the first search of this kind of signature at the Large Hadron Collider. In order to select an event, it is required to have a di-tau mass close to 125 GeV, and the tau leptons must have opposite signs. The BB mass ranges from 60 to 2800 GeV, and the tau final states must include one hadronically decaying tau. All of the tau leptons are identified by the deep tau algorithm. And furthermore, at least one B-jet is required to be present, selected by the deep jet algorithm. Several neural networks are then used to assign an event to the signal region or a control region for certain regions of the Higgs bosons. And different background estimation procedures are used depending on the final state. On the bottom, you see on the left-hand side the di-tau background, and on the right-hand side, the signal region, both in the tau E, tau H final state. And you see that with increasing neural network output, the respective contribution of background or signal is increased significantly, in this case for this particular combination of Higgs boson masses. As no deviation from the standard model is observed, model-independent limits are determined and combined for all the three final states. For capital H masses reaching from 240 to 3000 GeV, where only this lowest limit is unscaled, and the others are offset by respective factors to make them distinguishable. The limits range from 125 down to 2.7 femtobarn for various combinations of the Higgs bosons. And these limits can be interpreted in terms of the next to minimum supersymmetric standard model, as you see on the left-hand side. And the mass region excluded here on the bottom is based on the maximally allowed cross-section times branching fraction of the model. And this red area is where the decay would be kinematically forbidden. So this brings me to my summary. I presented various analyses targeting Higgs physics within and beyond the standard model. So far, all results agree well with the standard model predictions within their uncertainty. However, there are additional exciting analyses to be published rather soon, especially lots of run-2 Bsm results are still to come, and significant improvement in statistical precision is assumed to rise with the upcoming LHC run-3 and the high luminosity LHC. Thank you very much.
You can hear us? Can you hear us, Paul?
Ah, yeah, now I can hear you again.
It
was very silent in between.
On slide 16, I have a question. Yeah, I mean, this is in the future, of course. Now you're still looking for Higgs production and to pose some limits on standard model predictions. But I'm wondering, I mean, if you're looking at this tau final state, so this is the channel where you also showed results for probing the CP properties, right? So at some point, if you include resonances, you have a resonance going to two scalars. It would be interesting to see whether one can use similar techniques then to determine the CP properties of the scalars. So let's say retest the CP properties of this 125, for example, in this scenario. So do you know of any efforts in this direction to extend the single Higgs production to tau CP tests to Higgs production?
I'm not sure, I have to say. I think so far the main focus is to, well, observe Higgs production. But I'm quite sure that as soon as this is done, also further precision measurements will be conducted. And then the tau channel is definitely one of the best channels to do that.
I have a question concerning CP violation in H into tau plus tau minus. You said that pseudoscalar coupling is excluded, and yeah, based on measurement of the angular distribution of planes, decay planes, right, of those stars. I believe you could limit quantity that is a genuine measure of CP violation, that is a product of scalar and pseudoscalar coupling. That could be just a number that you could get from your data, I believe.
So, well, from this analysis, yeah, it would be, I mean, the result here is...
Yeah, here you say that it's consistent with standard model, which means that this product is limited, and that could be useful. Instead of excluding extreme cases, right, like pseudoscale.
Yeah, of course. I mean, it can be that at some point, I mean, this is the target of this analysis, right? It targets to either say, okay, we can say we have a totally scalar coupling, or we have some admixtures. If we find some admixtures of pseudoscalar coupling, then we have we have some beyond the standard model physics.
I also have a question related to this slide. So Probably it is written, but it's really very tiny. What is the uncertainty of the mixing angle that you measured?
Sorry, yeah, this is, so the observed result is 4 plus minus 17, and the expectation is 0 plus minus 23.
Thank you.
Okay, so I think we have to go on. So let's thank the speaker once again. Thank you for joining us, Paul. And now the last contribution in this session is by Ivanka Bokovic from University of Belgrade, and who will present us the results on the linear E plus E minus Higgs factories. So. You will get help from. Go ahead.
Thank you. Thank you.
Okay, so you have 25 minutes. Please.
Okay. Thank you very much. I think it's a really great luck that we had previous speakers talking on mainly Higgs physics at Atlas and CMS. Because I'm going to introduce future linear colliders as options for Higgs factories that basically can do the same, but hopefully better. Should I stop talking? No problem. Can I continue? Thank you. So, I mean, most of the people here are theorists, so probably I do not have to explain very much why do we need Higgs factories, but I will nevertheless introduce linear collider projects as a possible options, talking a bit on their detector concepts and technologies and what can be measured in the Higgs sector with these devices. Okay, because I'm experimentalist, I have naturally my favorite theorist, which is Nima Arkani Hamed, which I robbed by a few slides. As already said in the previous talk, Higgs discovery ended era of reductionism and symmetry in particle physics. So we observed a unique particle, never seen before, fundamental scalar unique in itself couplings, that basically opened two important questions of the nature of the relativistic vacuum. How can we accommodate it in the observed density of the universe, and why Higgs is not enormously massive or even Planckian? This can be formulated as a well-known cosmological constant and hierarchy problem, where Nima is here asking even more liberally formulated question: why is there a macroscopic universe at all? At LHC, we do not have new discoveries, so basically there are only limits improving with every run. And with the current resolution, for instance, to probe Higgs compositeness, the Higgs could be as point-like as elementary as pion. Also, even high luminosity LHC could probe Higgs self-couplings with 50% uncertainty. So being a harbinger of the profound new principles at work in the quantum vacuum, Higgs should be studied more closely. What brings us to the Higgs factories? Higgs factories are prioritized in European particle physics strategy from the last year as the highest priority future initiatives. There are several projects on the market, all offering millions of Higgs bosons. Some are linear, I'm going to focus on linear, ILC and click. Some are circular, CPC and FCCE. All electron-positron colliders comes with a set of advantages, like the initial defined initial state, which means reconstructible events from the first principles, also almost QCD-free environment. And what is a particular feature of a linear colliders is the accessibility of the high center of mass energies above TeV. This brings particular benefits when it comes to the measurement of the Higgs self-couplings and also Bsm signatures in the Higgs sector. At E+ E- machines, high precision measurements will be dominated by statistical uncertainty. It's clear that will be run for statistical precisions. The starting point is 100 times the LED luminosities. Of course, circular machines are in favor when it comes to luminosity, while a linear could address the higher center of mass scales. Everybody is asking a question: which one is going to be built, and is the physics performance will be the only one to decide? Of course, it's not like that. It is also the flexibility of the physics span. For instance, great advantage of circular colliders is that they can accommodate protons in their ring, while E+ E- could also give rise to a gamma-gamma collider. Also, then the flexibility to sudden changes, for instance, unexpected discoveries that the high luminosity LHC, then technological feasibility and cost, and I would say also politics, because building such a machine is has a flavor of supremacy in the field a bit as well. Linear colliders comes as mature technologies with a decade, in case of click, or even decades behind the ILC of vigorous R&D development. So they are ready to take projects. If we would have a decision to make these machines, they could deliver their first beams already around 2035. They all come at stage and upgradable machines, what basically enables various Higgs production mechanisms to be addressed. Higgs Strahlung at lowest center of mass energy, WW fusion enabling access to Higgs rare decays, and Higgs double production enabling measurement of the Higgs self-coupling. This is a nice example comparing Z-pole and treat TeV, how the less precise measurement at higher energy leads to the same precision of observables. So we really can strongly benefit from higher energies. Also from beam polarization, and this is illustration from ILC, that could in addition provide new observable sensitive to B physics, helps to characterize the newly discovered particles and thus discriminate between the Bsm models. And due to the chiral nature of WW fusion, you can almost double the luminosity with polarization. There are a few technical benefits. These machines are triggerless, and also the readout could be in the power pulsing mode. ILC is the oldest project, and I could proudly say that I was with the Tesla project, which was European project of the future linear collider already from 2000. Now it is merged from Japanese, American, and European project, where European Tesla technology developed at DAISY was adopted in 2004 by ICLA. This is a cold superconducting machine. It is staged. Basically, it can run from the Z0 pole and WW threshold for precision electroweak measurements up to where beam polarization is available up to 80% for electrons and 30% for positrons. The footprint for the first phase is 20.5 kilometers, and the site has already been chosen in Japan. It's Kitakami, where again with years of geological and similar surveys. I think the free electron laser, European free electron laser operating now as XFL at DAISY, is basically the largest ever accelerator prototype, where basically the full industrialization of the ILC-like cavities is demonstrated. This is a bit of history of the project, which is now in the phase that international development team is being built in order to prepare a laboratory in Japan. And as I said, it all depends on a political decision to build this machine. What is nice about ILC is that, like LHC, it comes with a set of auxiliary experiments, so which are non-collider experiments to study dark sector in the form of parasitic fixed target or beam dump experiment under the name of ILCX. Two detector options are being developed. One is ILD and the other is all silicon SID. ILD is mother of all detectors, because every future E+ E- project would start from ILD and then modified according to its conditions. It is optimized for center of mass energy from the Z0 production up to 1 TeV, and the particle flow is the key word for all these detectors, because only neutral part hadrons are left to less precise hadron calorimeters for determination. Everything else, of course, except for photons, which are detected in the eCal, comes in combination with the central tracker, leading to the jet resolutions between 3 to 4%, which is really needed to distinguish between Higgs W and Z jets. Another very interesting project, this is hibernated now at the moment by CERN, but unique in its feature to access 3 TeV center of mass energy is CLIC. Differently from ILC, it's a warmer machine, so normal conductivity, high current drive beam feeds the electromagnetic gradient to the main beam. And in the CLIC test facility at CERN, now operating, it's clear, the ability to reach 100 MeV, megavolts per meter gradients in the main beam cavities is being demonstrated. CLIC detector is again, as I said, started from ILD, but then the central tracker is replaced with silicon, so it's all silicon tracker. It's a bit more compact, again, heavily relying on particle flow calorimetry with the timestamp readout, which is in case of CLIC and not of ILC needed because of the beam-Strahlung interactions that are more pronounced in the higher center of mass energies. This project is also well documented in the yellow reports. The performances of all these detectors are similar. I already mentioned jet resolution, then it is excellent transverse momentum resolution for muons, which is crucial, for instance, in the Higgs-Strahlung for the recoil mass measurement, and again, excellent B-tagging performances. Although these projects will be Higgs factories, it's not only Higgs physics that they will address. So it is top physics from the top quark mass measurement, electroweak couplings up to its CP properties and Bsm constraints that could be preferably addressed at low or high center of mass energies. Also Bsm physics, which is with the preferred sensitivities at high center of mass energies, where it can be searched either directly or indirectly. This is a nice example for a Bsm indirect search, where, for instance, at the highest center of mass energies, you can reach the new physics scale at the order of 100 TeV. So these machines are really capable to explore the large span of energies. In the Higgs sector, where I'm going to focus that, the Higgs couplings are also the basics set of measurements, which can be measured in the either model-independent way, which is a unique feature of E plus E minus colliders, or in the LHC style kappa framework, or in the EFT approach. While Higgs self-couplings, or the measurement in the Higgs sector to probe either dark matter or Bsm in general, as well as CP violation measurements, are preferred at higher center of mass energies. As I said, various Higgs production mechanisms are available. This is the Higgs Strahlung, enabling measurement of in a model-independent way of the ZH cross-section. And most of the Higgs couplings can be determined with a better precision than at high luminosity LHC only from this phase. In WW fusion, you have really enhanced statistics. You can access rare decays. In double Higgs production, lambda can be measured. Linear colliders are benefiting from the accessibility of the high energy scale, from the polarization, and finally from combination of all these results with the different data polarization and within a staged approach. So even rare decays can be measured. You see that the branching fraction is of order of 2 times 10 to the minus 4 for muons. This is example from ILC of the Higgs to muon coupling, with the final statistical precision of 70%. There are less precise measurements from different data samples, so with different polarization at different energies are combined. This is example of a pseudo experiment where signal is fitted over background, while the statistical precision is extracted from the pool distribution of the repeated pseudo experiments. This is a comparison what can be done in terms of Higgs couplings at T plus T minus colliders with the situation at LHC and PP in general, where I emphasize again the high energy benefits I'm going to talk now. Okay, you are all theorists, so I guess that I do not have to spend much time on this slide, how well we need to know Higgs couplings. So basically, electroweak couplings of electroweak bosons are particularly sensitive to Bsm contributions, lambda even more, and apparently they have to be known at the percent level. And this can be achieved with already in the first phase of operation in the model-independent way. This is the example from CLIC, and this is the example from ILC, where we see that precision of Higgs couplings to electroweak bosons can be measured below 1% already in the first phase. The situation is similar also with circular colliders, and of course, everything is these machines are superior in combination with high luminosity LHC. I think this is a clear demonstration of such a synergy of a future E plus E minus machine with high luminosity LHC, where already the first phase leads to a huge improvements of high luminosity LHC accuracies. Here, in the case of CLIC, where you add up all phases in combination with high luminosity LHC, practically most of the couplings can be measured at the Fermi level. Now we come to maybe the most critical measurement, and this is Higgs self-coupling measurement. The previous speaker also discussed it. And it is, of course, quite important to know lambda determining the shape of the Higgs potential, but also receiving eventual contribution from Bsm models, or being significantly enhanced in the electroweak barrier genesis models and so on. WW fusion, where Higgs decays to a pair of Higgs, is apparently the most sensitive process, and it is clearly illustrated that sensitivity is rising with the center of mass energy. So it is no strange that CLIC actually could be superior by reaching 3 TeV in measuring the Higgs self-coupling below 10%. You see that high luminosity LHC cannot do more, or even high energy, because these measurements are constrained by by theoretical uncertainties. What is again a nice feature of linear collider is that you can combine double Higgs production in Higgs-Strahlung and WW fusion. So this is Higgs-Strahlung, this is WW fusion, and different behavior with respect to the non-standard model contributions helps to resolve ambiguities from interference. Also, what is, again, clear benefit from higher center of mass energy, by adding 1 TeV ILC, you get again at the level of 10% in lambda uncertainty. It is also interesting to see here if really lambda strongly deviates from the standard model value, actually linear colliders at high energies are again superior in determination of lambda. Then Higgs could serve as a probe to BSM. One way to look for it is in the EFT approach. Of course, the larger the precision, higher the lambda scale reach. So this is the result from ILC, where new physics scale up to 25 TeV can be probed from EFT fits. Some models which are in principle hardly accessible at high luminosity LHC, and this is deviation expected for the Higgs couplings, can be probed can be interpreted in the EFT framework. This is result from 250 GeV ILC, where most of the models can be discriminated above 5 sigma. Again, if you would combine high luminosity LHC plus high energy phase of ILC with polarized beam, there basically no model is left that cannot be confirmed or ruled out in such a combination. As previous speaker said, there are various ways for BSM to manifest in the Higgs sector. One possibility is that Higgs is composite. This is the high luminosity discovery reach. This is, for instance, the 3 TeV quick reach in depending on the parameter assumption. So high scale really can be probed. We see here up to 50 TeV. Also, in many BSM models, standard model Higgs come with initial scalars that could be light, and this is example of their spectrum from ILC, or that could be heavy singlet state mixed within standard model Higgs with a mixing angle gamma that again click at the highest energy could probe superior in comparison to, for instance, LHC reach. Also, if dark matter is massive, as pointed out also by previous speaker, it will be connected to the standard model particles and also to Higgs that could decay invisibly, and by looking into the recoil mass, that nothing is basically recoiling against the primary Z boson in Higgs-Strahlung, you can measure the Higgs invisible branching ratio. This is from ILC, where in the full run, you can access it below 0.5% precision. Also, CP violation, CP symmetry can be violated in the Higgs sector. Higgs can be a mixture of scalar and pseudoscalar states. We saw exclusion of the completely odd CP state, and also uncertainty of 23% from the current CMS measurement in the previous talk. These are projections for future projects. High luminosity LHC could reduce uncertainty to 8%, while ILC can measure it down to 4%, again in the Higgs to tau, which is receiving contributions at a 3 level. So it is the most favorable channel. Again, angles between production or even in the Higgs decays between decay planes can be found to fit psi from the angle between the planes. If such a pseudo experiments are repeated, and this is example from ILC Higgs to tau measurement, the psi can be extracted with this final precision. What is interesting to see to say is that also Higgs vector boson vertices can be affected by this type of mixing, and that there is a lot of Higgs production and decay mechanisms to probe it. There is ongoing analysis of the Higgs production in ZZ fusion at ILC, where not only fermionic but bosonic vertices can be probed in terms of CP violation. Of course, everybody likes to compare everything between projects, linear versus circular, lepton versus proton, and so on. So I try to do a fair comparison here, which is again personal view. Precision-wise, linear circular colliders are comparable when it comes to the Higgs couplings. But due to the high energy excess of the high cross-section production mechanisms, you can measure rare decays at linear collider, you can superiorly measure Higgs self-coupling, and you have enhanced sensitivity to the Bsm contributions in the Higgs sector. Great advantage, at the other hand, of the circular machines is the extensibility of the Higgs span. You can insert proton in the same tunnel and boost them to 100 TeV center of mass energies. When it comes to the prediction and future 100 TeV hadron collider, there are a few open issues at the moment, like the accelerator and detector technologies, the huge pileup, which will be of order of 1,000. So one really have to think how to reconstruct events under such experimental conditions, and the control of theoretical uncertainties. You all know this better than me, and I just like to point out that significant amount of work in theory is needed in order to improve PDFs, improve non-perturbative calculations, and so on, needed for instance, FCC HH at the level of 100. So you have to improve the 100 times the current theoretical uncertainties, which is quite demanding and presumably requires years of work on it. I'm coming to my summary. I hopefully convinced you that all future E+ E- projects bring significant added value to the projected high luminosity LHC sensitivities in the Higgs sector. The feature of E+ E- machines is our measurements in a model-independent way, where the highest center of mass energies bring added value in terms of the Higgs self-coupling measurements and sensitivity to the realization of Bsm scenarios in the Higgs sector. I have basically two main messages. One is that upgrade is important, that these machines should not serve only at the first stages as a Higgs factories. High center of mass energies are genuine advantages of a linear collider, and basically they are ready to wear projects if there would be a decision to have them. Thank you very much.
Thank you very much for a very interesting presentation and keeping time also very well. So we have time for questions. I'm sure there are some. Okay, so we can start with the online one. Paul, yes, please, Paul.
Yeah, so thanks a lot for this very, very interesting presentation. And coming from the Higgs physics myself, I'm quite interested, of course, in everything that can increase sensitivity there. So perhaps you mentioned it and I didn't get it, but first, how likely are these two ILC and CLIC projects to be realized, and probably also is there kind of a timeline? And second, how is it done with the detectors? This is technical, but I mean, at the circular collider, we have several interaction points, but for a linear collider, I assume there would be only one, right?
Yeah. Okay. Let me go to one of my previous slides. to answer about the timeline. First of all, thank you very much for your question. So you see, both for COLIC, which is somewhere here, and ILC, which is on the top, we have basically the same timeline, allowing 7 to 9 years for construction after the approval of the experiments. So this sets, I would say, the time scale. About the detectors, as I said, the linear collider detectors have been studied already from the beginning of this century. So behind the ILD, and let me find it, it is here. You have from Tesla TDR, you have already 20 years of vigorous R&D using the existing technologies, prototyping, test beams, and full simulations in the physics studies. So if there is a detector which is very well known and described and also technologically available at the moment, I would say it is ILD detector. But the same is true also for CLIC, that basically modified design according to their experimental conditions and replaced TPC with old silicon tracker. So detectors, I would say, are including the R&D. I didn't give any slides on that, but if you look into the reference, you can find it, because mostly people are theorists, so I really did not want to go into technical details of the test beams and detector performances, but I think they're really ready to go projects. And about the interaction point, I think this is the most critical questions when it comes to linear machines. ILC is currently foreseen to operate in the so-called push-pull mode, where both detector concepts could be run as independent experiments. If it comes to the positive political decision by the Japanese government, I'm sure that if this question will be addressed again, and maybe the answer would not be the same. But this is the current paradigm push-pull.
Banka, I have a question concerning ILC.
Okay, sorry.
Is there E minus option still on the table, or it is completely forgotten now for higher energy stage? E minus option.
Yes.
Is it still being considered, or it is?
I would not say it is at the moment on the table, but maybe Philip, you can.
I think it is somehow now being discussed again. I know at the workshop which is coming in October, I think that it was mentioned that there will be a dedicated session where these other options will be discussed.
Yeah.
So it's reconsidered now, as we are entering the phase where the project can basically make a large step forward in the near future. All the possible options are being reconsidered now.
Yeah, I agree with that. I mean, there was not a relevant R&D activity up to now, but as Philip pointed out, as ILC is getting more serious, and hopefully it is, then other options are also discussed. Also gamma that I mentioned previously.
Okay, so the last question.
Do other options include backscatter laser beams?
Well, this is what Ivanka mentioned, gamma. I think it's much more difficult. So it was mentioned, but I think it's much more difficult than E minus. I would not be very optimistic, because it requires really large changes to the machine.
I think at this point we see difference between theory and experimentalists. We experimentalists would be tremendously happy P plus E minus is improved. But since your imagination is much more developed, you're already thinking about E minus, gamma. But I believe, as Philip already said, once the ILC got approval, these options will be also discussed for sure.
Okay, so now the very last question.
Yes, on the question of the E minus, E minus, historically, this has been considered at every E plus E minus collider in the last 50 years. It hasn't actually been done since 1971 at 1.1 GeV. But since there is some interest in bileptons, which decay, have a mass of allegedly a TeV or something like that, that would be ideal so I think it should be reserved. Certainly, if the LHC finds a doubly charged bilepton, then obviously it would be a bilepton factory if you had that sort of thing. So the interest might suddenly increase in the near future, hopefully, or not. But it's certainly of interest.
Of course, thank you so much for your comment. I think that I believe that we have people in our community who are aware of that and who will advocate for that option.
Okay, so let's thank Ivanka for all the speakers of the morning session again. And we now have a coffee break. Thank you very much.